Bernardo, and today I'm going to present part of my PhD at the Instituto Nacional de Pesquisa da Amazônia, in Brazil, which is estimating Amazonian rivers as barrier across time and space within widespread bounds. So a lot of people know that in Amazon we have the biggest biodiversity in the world, and a lot of researchers are trying to understand the process related to this biodiversity. So, for example, we have climatic factors where Hafer proposed the hypothesis of refuge in Amazon. So during the glacial periods, we had fragmented islands along the landscape, but recently Chang said that only the East Amazon was fragmented and the West Amazon was a continuous forest. So we have also the river barrier hypothesis, which has been tested for different rivers and also different groups of species. And Wallace was the first one that observed different species of primates in different sides of the river, but was Hafer, in his words, that he proposed the river as responsible for generating this diversity. So the river can act in two different ways. For example, as a primary barrier, which is responsible for allopathic speciation, which sister species in different sides of the river share common ancestral, and it's probably a congruent event for more than one species. So the divergence time we probably is going to be the same for more than one species. And in this case, the river is responsible for generating the diversity. The river acting as a secondary barrier, we have a no congruent event between the species. So it very depends of the ability of the species to disperse along the landscape. And in this scenario, we had the rivers coming first, emerging first, then the species. So the goal here is test how the main Amazon rivers had acted as a barrier for population divergence along time, space, and species. So we tested seven different rivers, main Amazon rivers, which are Tocantins, Xingu, Tapajós, Madeira, Caminhões Negro, and Amazonas. And we tested for two broadly distributed species with different ecologies and habitats to avoid geographically limited tests. So the first species is Gonatodes humeralis. It's a small lizard widespread in Amazon, so we can find different habitats. You can find close to the roots of the trees and also close to small communities. So just here the map with the distribution of these species. And the Dendropisophis leucophyllatus is a tree frog, and also associated with low float plant forest and also upland forest, which we can find close to the ponds. And it's some papers came saying that Dendropisophis leucophyllatus is a paraphyletic species. So in my other chapters from my thesis, I worked with the group. So all the lineage, we did a phylogenetic analysis. So all the lineage that came as a Dendropisophis leucophyllatus, we use it for this work. So we had two libraries for each species. We used DD RegSec protocol, and all my data was generated at the University of Michigan. We used stacks to analyze the data. So we have for Gonatodes humeralis, 106 individuals, around 28,000 SNPs with 10% of missing data. And Dendropisophis leucophyllatus, we have 99 individuals, 120,000 SNPs, and 20% of missing data. And here is the map of the distribution of my samples. So we divided the populations as here. Each color is one population, and we use the areas of endemism proposed in the Amazon for each population. And then in each one we calculated the nucleotide diversity. And between populations we calculate the genetic diversification using FST. So for the divergence time, we use fast simple. So we tested two different models: the migration model, the A, which we have population size A1 and 2, and the ancestral population size, and also the divergence time and migration between them. For the first model and the second model, we have no migration. So how we calculated that? So for example, we have Belém population, and then we have Xingu population, and between them we have the Tapajós River. So for this river, we tested model A and B. So we did that for all the rivers. So we had Tapajós, Xingu, Tocantins, Madeira, Solimões, and Negro. And for the Amazon River, which Guiana population has border with 5 other areas, we divided the Amazon in 5. So 1, 2, 3, 4, 5. So total we have 22 tests and 11 for each species. So as a result, we have for the population in the axis we have the populations, and the y-axis the values. So as you can see, we have close related. So close values for all these similar values for all the populations. Only in Ambali and Nepal we have high values for the frogs than for the lizards. The FST, the genetic differentiation, we have the y-axis this parts of the rivers, and then the y-axis the values. So as you can see, we have more values, higher values for the lizards, for the frogs than for the lizards, and only Solimões and Tapajós, Solimões and Madeira, we have close values for them. So as you can see, the river act in structuring population genetics. And for the migration model, we found very low values, or most of the time 0. So we concluded that no gene flow is going on between populations. So for the divergence time, we estimated the model, the no migration model, for all the rivers. So here we have the divergence time. In the x-axis we have the rivers, this part of the rivers, and the y-axis we have the time. And as you can see, the oldest time, for example here, it's around 120,000 years. So in terms of history of Amazon, it's very recent. So we have very recent times for both species. We have no similarity along divergence times, except for the river Xingu. We have older times for the Drosophilus leucophyllatus than for the Gonatops mineralis, and the divergence time didn't follow any order along species. So if, for example, the species start to disperse from, for example, the Belém population, and for the rest of the Amazon, we expect order in the time of the rivers, and we don't have that. So because the time is very recent, we can conclude that the river is acting as a secondary barrier. Even if the river is acting similar for all is acting as a barrier for all the rivers, we can see that the time change. So for example, in the Xingu River, maybe characteristics of this river can affect the populations at the same way. We don't know. And also, we have older times for the frogs than for the lizards. Maybe characteristics of these species is affecting, like ecological characteristics, maybe affect this time, the difference that we have between these species. So we know that now we don't have gene flow going on, but in the past we had. So we don't know how many times it happened in the history. So probably cycles of connection and isolation best explain our data. And also the river's dynamic, we know that had been changed along the time. So we know that the rivers change the course and also change the landscape. So it also can affect our results. So as a conclusion, all the tested rivers are acting as a barrier for population divergence along time, space, and species. The hypothesis of cyclical periods of connection and isolation best explain the history of those taxons. And the river may act as a much more dynamic barriers than we thought before, that the river was only responsible for generating the diversity. So I would like to thank all the authors of this paper, Werneck and Leit's Lab, and also No's Lab, for all the support. All my financials and also the Evolution Meeting for the award. And here are some of the collections that gave me the samples for this work. So thank you everyone. I'm happy to answer some questions.
Since you know some of the places where the rivers change course, were you able to sample from different places on either side of the various places the river might have been in the past?
Oh, no. I mean, no.
Yeah,
No.
because you could see different amounts of gene flow depending on which part of the change course you were able to sample.
Yes, but no, I didn't. Because, yeah, no, I didn't do that, but that's a good thing to do.
Oh, I'm sorry. Hey, man, how are you? I'm to navigate. Good to see you. I was there.